you've all been exposed to it. I'm just going to try to relate some of the mathematical bases that we use in applied geophysics, at least at a fairly basic level. And unlike your math classes, I'm just going to talk about the grappa that you need in applied geophysics, kind of boil it down to the really germane stuff. Okay, so let's start with vectors. We're using vectors all the time in geophysics, as you saw with the equations of motion and the diffusion equation, the wave equation. All of these physical quantities usually have direction. Gravity has a direction, right? Gravity points toward the center of the Earth. Magnetics has a direction that we'll see. Interestingly enough, the magnetic field can point in different directions based on where you are relative to the equator. At the poles, the magnetic direction is exactly the same as the gravity is, pointing toward the center of the Earth. As you get to the equator, the magnetic field is actually pointing parallel to the surface of the Earth. Okay? And then it varies as the cosine of the angle as you move from the poles to the equator. So vectors are quite important in geophysics, just in those two quantities, beyond other things. And in our seismic work, a lot of the seismic research that is going on, we use vector fields to define, to separate or characterize certain wavetypes. So, scalar quantities are quantities that have magnitude only. There is no direction associated with them. If I were to give you gravity, is gravity a scalar quantity or a vector quantity? It's a vector. It's a vector. What about gravitational potential? In other words, some kind of surface that has equal gravity. In that case, the gravitational potential is a scalar quantity. It's basically always pointing in. So scalar quantities obviously will not have gradients in certain directions. Right? They won't have curl. They'll basically only, they won't have direction. Vector quantities have both a scalar component and a direction. Examples include displacement, velocity, acceleration like gravity, momentum, angular momentum, electric fields, magnetic fields, dipoles. You have to have an orientation of a dipole, a vector quantity. Tensor quantities, even more complicated. Rather than looking at a vector with like x or I, j, k, we look at a function that has two quantities. For example, let's say that we have a square here. Okay, so this is the, let's say this is the z face. This is the y face of the square, and this is the x face. And let's say that I apply a force in this direction to the y face. All right? That has two components, right? It's a force applied in a certain direction to a certain face. I could apply the same force to the z face. I could apply the same force to the x face. Right? So I could look at these as F, and let's say we're defining the force as the perpendicular. So this is the force in the y direction. This would be F, y, y. That's the force applied to this face. I could have this one, that's F of, let's say, zy. So this one indicates the face, and this indicates the force group all those together, what do I have? If I look at all the different force directions on all the different faces. Now obviously I could have, by symmetry, I could have the force on the minus x direction, but it wouldn't make any difference, right? There's symmetry there. So what do I have? How big is this force tensor? If I look at all the different force directions and all the different faces, and assume symmetry. Anybody? None. Exactly. I'm basically going to have a tensor that I'll call f of ij. Okay? And f of ij, I could erase some of this. F of ij is going to look like this, right? It's going to look like f of xx, f of yy, f of zz, f of xy, f of xz, f of yz, so forth, right? So that is f of ij. And that's what we call a tensor quantity. Okay, so if we're looking at representing a vector, we basically do it as an arrow, as you all know. And if we're adding A and B together, this is A, this is B, we get basically the bisection of the parallelogram. If we have the same vector A and B, and we basically say A minus B, I always think of it as what do we have to add to B to get back to A. So we have an arrow going back to that point, which is essentially the other bisector of the parallelogram. So that's addition and subtraction of vectors. Obviously, we have all kinds of different ways in the literature or in your books that we can represent the vectors. We can basically take a vector, and vector A in a certain direction has an x component, a y component, and a z component. We can also define this vector based on direction cosines. In other words, the angle that A makes with each of the axes. So in this case, we're going to call alpha the angle that the vector makes with the x-axis. And if we took ax, or A cosine of alpha, we would basically get the ax component. Beta is the angle that A makes with the y-axis, and gamma is the angle that A makes with the z-axis. And those are called direction cosines. So, and they all basically have magnitude of sum together of 1. We can always basically take A and separate it into the magnitude of A and a direction and a unit vector in that direction. And we can call the unit vector x hat. Usually the hat indicates a unit vector. We can call it ijk. For algebra, especially when we get into larger number of dimensions, you can imagine that in physical quantities we're looking at 3 dimensions. But what if, for example, we have time as a fourth dimension, right? Or we have some nonlinear space. We could have e's going past the 3 physical dimensions of x, y, z. So for algebra and for understanding more complicated spaces, we often use these e values or some kind of unit vector in both physical and other dimensions. So what can we do with vectors? Well, we can multiply vectors by constants. If we multiply the vector x by A, we can represent it as alpha, that's alpha x1, alpha x2, alpha x3. We can add vectors. And what we do there is we simply add the components together. We can also take the magnitude of the components of a vector. Yeah, basically the norm or the length of the vector. Okay, so one of the big things that we do in using vectors, particularly in geophysical techniques where we're